We've been talking about domain and range, and yesterday we talked about domain and range of a discrete function or relation. So today we're going to talk about domain and range of continuous functions. As we've said, domain is x, range is y, and discrete meant disconnected functions. That would be separate points or dots. And continuous today is connected. So whereas discrete was disconnected, our separate dots on the graph, points on the graph, continuous is connected. So they're going to be connected points on the graph. So let's look at a couple of examples. So the first kind of example, there's different kinds of continuous graphs that we do domain and range on. So the first ones that we're going to look at are the ones with endpoints. They have a start and a stop. This one has a start and a stop, but it's what we're looking at here is we want to talk about all the x's in this function. This one is a function. All the x's, that means it includes all the x's along this line. So there's way too many to count. We can't count the x's like we can or just list them like we did on a discrete function. So let's look at the boundaries. Because all these little x's, decimals, fractions, everything in between are included. We can't list them all, so let's look at the boundaries. Let's talk about what is the smallest x ever gets. Well, this negative 2 is like a left boundary. There are no x's less than negative 2. Over here, the right boundary would be 4. That's the biggest x ever gets. It never gets bigger. So all the x values between negative 2 and 4 are included on this line, this connected graph. So we have to find a way to show that. So we know that domain's all the x values. We know that it can be less than or equal to 4 because 4 is our top boundary and it's colored in, so it includes 4. That's why we get the equal to. But we also know that all the x's are greater than or equal to negative 2. So if we write it like this, we're still doing what we did on discrete yesterday. We're going least to greatest, smallest to the biggest x value, but we're showing that all the x's in between are included. So let's talk about our range. Our range is our y values. So the smallest, the lowest that y ever gets is negative 3. And then the biggest that y ever gets is positive 4. So all of the y's on this graph fall between negative 3 and positive 4. So we would write it like this. This is for endpoints. One strategy that seems to work well is that you kind of make a box around this on its boundaries. So I box it off at the leftmost, rightmost, top, and bottom. Then where my box crossed the x-axis, those are my x boundaries, my negative 2 and my 4. Where my box crosses the y-axis, that's my y boundaries, my negative 3 and my positive 4. So let's try another one like this. This is one of those that has the endpoints. So what if I did my box strategy here? Here's the left boundary. Here's the right boundary. So this boundary crosses the x-axis at negative 2. And over here, it crosses it at, well, I'm going to have to count. These numbers are too little. 1, 2, 3, 4, 5, 6, 7. So negative 2, positive 7. X goes in the middle because it's all the x's in between. And I always have less thans because I always go least to greatest. And because the points are colored in, I get the line under it for the equal to. So if I go to the bottom and the top and put my boundaries, I can see that the bottom boundary is at 1, 2, 3, negative 3 on the y-axis, and the top boundary is at 6. Because it's the range, it's the y, so that values y goes in the middle. Because I did least to greatest, I get less thans, and because they are colored in circles, I get or equal to under it. So I think the more you do of these with the end points, the more you're going to see the pattern. So over here, this one is got the endpoints again, but this endpoint is colored in. This one's an open circle. So I can still do my box. I can still use my box strategy here. And you can see that this side of the box goes through -2. This side goes through 4. So my x boundaries are -2 and +4. Since now I always have less thans because I'm going least to greatest, this one's colored in. At the -2, it's colored in, so it gets a line under it. But at the +4, it's open. It does not include 4, so I don't put a line under it. It can't be 4. It has to be less than 4. Then on my range, I'm going to do my bottom boundary and my top boundary. I'm going to get -3 and +3. And which one's colored in? The -3. The +3 has the open circle on it. So there's my domain and range for this one. I'm going to skip these two in my booklet. I'm doing this little booklet that you can find on Canvas. So I want to skip to the last page. This one's also an endpoint one with one colored in and one open. So if I do my boundaries, I'm going to see that x goes from 1, 2, 3, 4, 5, -5, to 1, 2, 3, 4, 5, 6. The -5's colored in, the 6 is not. My y goes from here to here. Now you will notice there are no dots here, no colored in or open circles. So let's talk about that. 1, 2, 3, 4, 5, 6. This is at -6. This is at +2. So in Algebra 1 especially, it's going to be very, very, very obvious to you if this value is not included. You will have the open circle. If there's no open circle, if they don't make it obvious to you that it doesn't touch that, then assume it touches and it gets the line under it, the equal to. We're going to assume this goes all the way up here and touches this because they didn't make it obvious that it doesn't. So at this point, I think we've seen several good examples of the endpoints. So now let's talk about when there are arrows involved, because that gets a little different. I don't have, on this one, you can see that I have a left boundary for x, but I don't have a right boundary. It goes forever and ever and ever to the right. When there's one arrow, I'm going to have only one number. Here I had 2 endpoints, so I had 2 numbers. Here I have 1 endpoint and 1 arrow, so I'm only going to have 1 number. So x only has 1 boundary, and it's at 0. Now, here I have a choice to make. Because there's only 1 number, I'm not going to least to greatest. I have to make a choice. Is x getting bigger than 0 or less than 0? Well, you can tell that my graph is going this direction. X is just going to keep getting bigger. It will never go over here less than 0. So in this case, all the x's greater than or equal to 0 are in my domain. Let's look at y. Well, 0, 0. 0 is also the boundary for y. Y never, this graph never dips below 0, so it's going to keep going up and up and up and up. So all the y's greater than or equal to 0 are in the range. So you can see that when you have an endpoint and an arrow, you have something a little bit different. So then here's an even different one. When you have 2 arrows, something's going forever and ever and ever and never stopping. It might be both, domain and range, or it might just be one of them. So let's look at x, domain, first. If you look at this graph, it's going to keep going this way, and it's going to keep going this way. There's no boundary to the left or right. You can't draw a box on the left or right. That means every conceivable x value can be in this function because it's going to go forever. That means every real number is a possibility. So we're going to do this big, funky looking capital R that stands for all real numbers. So every time you have two arrows, something's going to be all real numbers, either domain or range or both. In this instance, though, it's not both because y has a boundary. Y only has one boundary, so it only gets one number. Its bottom boundary is at -3. Y never goes, this graph doesn't go below -3. It's going to go up and up and up and up forever. So y is all of the values that are greater than or equal to -3 because of this end point that's colored in at the -3. And I'm going to stop this video so that it's not too long, and I'll make another video with some more examples for you.